Hey, what's up YouTube? So here we are back again. So we're on the HVAC Optimal Start Math Playground. Once again, we're studying mechanical engineering theory for the mathematical models defined in research that output minutes to warm up or cool down a zone. So these mathematical models, they sit in the building automation system somewhere, and you feed in zone temp data, occupied zone set point data, and then some data of when the building is scheduled to start for the building occupancy, and these different math models will output minutes to condition the zone. Once again, like, this stuff lives deep inside the building automation system. Typically, building automation technician would never be making these models. They would be using some kind of a widget that has these mathematical models built into the firmware of the building automation system. But there could be some instances where in smart building IoT that the IoT platform does some of this stuff. So it could be used in a couple different places. So we're kind of deeper down into this course already, Model 4, where we've studied the Model 0, which is typical, just a linear degree per minute model. Model 1, which is a quadratic regression on the zone temp and set point delta difference. Model 2, which was Model 0 plus the ratio, some kind of a ratio defined that incorporates outside air temperature. Model 3, which was a multiple linear regression model defined in the paper, where our bonus days on our AI generated coursework, we were doing some of the matrix math by hand, which all the matrix algebra could have been its own college semester, but in a 20-minute mini lesson, we did the best of our job. And then we're on Model 4 for this first order physics driven model. So in the paper, unable to render. Usually we're able to render this. Wonder why it's not able to render today. But so this is the paper that really smart people, Serena Boss's crew at P&L wrote, defining these different models that apparently are used in industry a little bit, probably in firmware of a building automation system, that they're a resistance capacitance type model incorporating the thermodynamics of a building. So check it out. Check out the paper. The different equations are kind of spelt out like this. And we're on to where are we? We're on to Model 4, which is a simple first order response model, an iterative model where it uses a little bit of log mathematics. So let's get out of that. And then we're on bonus day 13, where, if you guys remember, I think we got up to around this range, and then there's just not enough content. I thought this coursework would be kind of basic, but it's actually kind of complex. Like, it's upper graduate engineering coursework, I think. Like, someone could do their whole PhD in this alone, I feel like. So, yeah, it's a little more complicated than what I originally went into thinking, but yeah, I'm learning something too, and hopefully you guys are as well. And like, something else that I'm doing too on the Vibe Coder repo, which is the Niagara-based building automation system for Optimal Start. I've been vibe coding, putting all of these different models into a Java widget. So there's 1,000 lines of Java running behind the scenes in here, where I'm using all 5 models in this block. And then the block has some features where it will, the model with the best average squared error over time, which I'm getting the best average squared error out of Model 2, which the paper said Model 3 is what they thought had the best. but I'm actually getting best performance out of Model 2. So as you can see, like this would be like what a building automation system would look like. You wire in a sensor reading for outside air temp, schedule next value, schedule next event time, and then the model would be predicting minutes if we were predicting right here, but we're not. And then we recorded our last run of warm-up. So there's computer science patterns in here that are recording starting the building automation system, and then it'll snapshot what that zone temperature was at that point in time, and then also the target zone set point. So then it's where we've been using the delta temperature, it's called, of the zone temp and target zone set point. And these different math models defined in research have a variety of different ways to predict minutes. So that's what it kind of looks like in a building automation system. This is just like a concept idea in a program object, where in the Niagara building automation system, I can run my own Java code in a block, in a widget, which is kind of rare. Most building automation systems, you don't have the ability to have Python or a Java or a higher level language at all. But if you ever wanted to see like what all the Java looks like, it's in the link here, and it's working. It appears to be working. So this is something I've put a ton of time into, in like slowly morphing it into a block that started out with just the simple with a simple linear degree per minute model in Java and predicting minutes, to slowly morphing it into all these different models, all with AI helping me write the code. So yeah, it's been interesting. It's still a work in progress. So it's been kind of fun. Any Niagara programmers, please reach out if you want to try it. You can download pre-built, pre-compiled BOG files here. And then this repo also has an agent's markdown sheet. So you could feed into ChatGPT or Gemini or whatever you want to use, all these different markdown files, and then the agent one, and then the AI has context to help you write whatever kind of algorithm you want to write. Okay, so where are we? So we're hopefully not getting off in the weeds here, but bonus day 13. So guardrails. So like something that the Java blocks I was just showing you has lots of guardrails built into it, and exponential moving average smoothing. So it if the model predicts something or some parameter gets updated, that it doesn't have a wild update into it. It's kind of slow and smoothed out to keep predictions kind of running smoothly. So, okay, so we're on here. Let's copy our code. This is our little script we were working with yesterday. So, and that when AI generated this course, it put in this little helper file, which is kind of cool. But I kind of like to see like what that code looks like. So, pretty basic stuff here. So we're just calculating an average or a mean based on the data. So this will feed in this whole list, different data points here, where in the Java code of the program object, this should be a full-blown array. But Python doesn't support arrays, a true array, unless you use like the NumPy computing library. So this is just summing all the values, taking a mean average. There's also a clamp. You feed in a high and a low value. And then there's also this exponential moving average, which we've talked about a lot previously, especially Model 0, like Model 0, exponential moving average. Pretty simple math right here. So it's just it's our previous value plus W, which I think is just a weight, a learning weight, and then multiplying it by the new value minus previous value. So it's just a way to do an exponential moving average, where if you adjust the weight, you'll get a little bit faster averaging. And here's this safe log. So this is just a way, I guess, to compute log with a math library, and you would feed in a max value, I guess. And then this was also our model 0. This was the iterative part of it, where we loop through all of the data and then we solve for C. So this is our equation. So C is the sum, and then there's an alpha A parameter in here somewhere, and then we divide by some numbers to here. So this computes C, value C by iterating through the data structure, and then this will compute model 4 with log math. Kind of an interesting way that they're just putting in like these maximum values, clamping it, and having some guardrails. So I think this is like what this is trying to account for. The only thing that was kind of confusing to me is like if these daily estimates, if these were, remember we were talking about if these would be, because a lot of times we have to calculate the delta temperature per run and the outside air temperature per run, and then we save these in a data structure. But I think that these would be errors yesterday on an index. So basically, like when we ran our optimal start, like our delta temperature was 6 degrees, and then 5 degrees, and then 4, and 3, then 2.5 by 1, and then slowly got up to zone set point. And over the course of 1, 2, 3, 4, 5, 6, 7, 8, 9 minutes. So this would have been a 9-minute warm-up cycle. And this we would have been recording our temperatures there. And then when we feed it into our least squares, we're computing like the error between each one of these numbers, and then solving for C in least squares. It's like, I think it's like regression, but in an iterative way of solving for it. I might just change some of this stuff, so we could even so let's just play around with our code. Okay, so C exponential moving average. Maybe we could even just say, oh, okay, so C new in errors yesterday. So I know that what they're trying to do in this lesson is they're just trying to clamp values and take an exponential moving average. Like, I might even use AI to clear up some of the confusion. So let's see. So this is day 13 of our bonus material. Okay, so here we go. Day 13, maybe we can do 14 today too. So I'm trying to play around with the code a little bit for the mini lesson. on day 13 instead of the, whoops. What would that code base look like? Also, these types of values would be delta temp errors in a single warm-up run, right? Per unit of time until reaching deadband. Alright, let's see what AI has to help us in our mini crash course. Since we don't have a full college semester on this, let's help with AI to help understand it. So yes, okay, yep, you're mixing two different lists in your environment, and what's tripping you up, day 13, is for daily estimates, not temperature errors. So, oh, okay, so they are C values, dimensionless decay ratios. Okay, so each warm up. Okay, so I just want to say, what would the completed script look like defining, differentiating C values and warm up temps and leave out any data that is not needed. For example, if we only need C from yesterday, don't include temperature data if it is not needed. So let's just see what that would look like. Okay, so I think, yeah, so maybe C, the temperature data is not needed. I might have misspoken on that. Guardrails. Oh boy, no, the script is getting even fancier. Alright, so it does get kind of confusing here, I think. Gosh, there's just so many comments from, it's like how, one thing I don't like about AI sometimes is like there's so many comments in the Python script that it almost makes it hard to read. Okay, so we got our clamp EMA safe log, we understand that. This is our least squares iteration to compute C. And then this is our math equation defined in the paper with the log math of A divided by B, the log of that divided by the log of C. Alright, and they're doing, some, so this is what I was most interested in, was errors yesterday. Okay, so this would be our max warm-up time. That is our exponential moving average weight. That's our zone temperature deadband. And this is our exponential moving average, our C, value of C. Okay, so yesterday, only data we need to learn new C is errors from yesterday. Kind of confusing, but I think I'm getting kind of the basic message of it. So ultimately, we're producing 6 point. I still think they wrote this really confusing. So basically, we do need this from yesterday, the errors yesterday, to compute a new C. And then we take the compare that to the current exponential moving average of C's. Okay, so basically we still need our errors. So this would be units of temperature. Then our moving average of C, which can be updated every day, is dimensionless, whatever that C units is. So I think I am kind of understanding it. It gets kind of confusing. Hopefully you guys are understanding this too. So just to say like this, just to iterate even further, so just triple check this would be degrees in units. Yes, triple checked. Those values are in degrees of temperature, degrees per time step, just like we talked about. So zone temp deadband is 4, our errors yesterday. So this would be what our computer science pattern captured, the zone slowly warming up, like we talked about. If this was captured every minute, that could look like it would in real life. Time delta today. So confusing. So basically, to run this full model, we would need our errors. We would need this data from yesterday, our current value of C. Yeah, I think it's making sense. Hopefully it's making sense to you guys too. And I think we'll walk over a little bit of the next. I just want to see increase W to 0.8. What happens to stability? Maybe we'll just do this little micro lesson, what we should have done all along. So I can just do lessons. Okay, so then it asks you to increase W to 0.8. So that's our exponential moving average weight. And you can see that it's computing slightly different moving average. What happens if you decrease it to 0.1? So this will have a slightly different effect on the C parameter. So it's to keep things stable, smoothed out in the data. Yeah, and then this is our clamp. Obviously prevents, which we definitely have an optimal start, is like guardrails in there to prevent the HVAC system starting 6 days early. Some wild numbers. I clamp mine to like an hour, like 90 minutes, an hour and a half. The HVAC system should never start. Maximum, depends on the system, should never run longer than 2 minutes, 2 hours. I mean, typically an hour is fine for maximum value. Okay, so then this is our full Model 4, our last day of our bonus section, is just our Model 4 actually I don't have this script. I thought I had this script. Oh, this is it. Okay, so here we go. This is kind of confusing, so I think I'm just going to cover this. It's basically kind of just at a high level of like, what we're doing. Like here's a max minutes, maximum 180 minutes. Here's our C min and C max values, which we talked about. So if it's in a cooling mode, some of the earlier lessons, we calculate cooling like this, or if it's a heating mode, then we calculate our air like this. And then this is where we would be estimating our or estimate our C value with that iterative approach, clamping it, and then we then run an exponential moving average across our new C value, our old C value, and then we pass that into and then to compute our current minutes. So suppose we could even try this. This would be paste. Whoa. Copy. So this would be lessons. It didn't print anything. Whatever. I think that's fine, because like the whole point of these exercises was just to get a little bit deeper into the weeds of Model 4, which I feel a little better than prior to this. So I think the next couple of YouTube videos, like we talked about, will still be Model 4, and then but we'll be using more of like the Python libraries for math. So if we wanted to see sneak peek at like more looks like it's the same kind of code base. Yeah, so Model 4, we're just kind of using the same thing. We'll be kind of using just slightly different code bases. So alright guys, I think this is all I have for today. We're still studying math equation 4, so a little confusing today. Sorry if it was kind of jumping around all over the place. I'm still trying to soak it in, so let's keep going with this, and then maybe we can just have, finally let it soak in. So it takes a little bit for, at least for me, to get this stuff to be like, okay, I finally get it. And I think I'm about 90-80% there. So thanks for joining me today, and I'll see you guys for tomorrow.